condensing. All right, so Chapter 7, Gravitation. We're going to talk about planetary motion and gravitation today, 7.1. That means we'll calculate gravitational force, talk about Kepler's 3 laws, and calculate the period of orbit of a planet around something, or even a satellite around something. It works for really anything. Let's talk about the history. It has a very rich history. First of all, Nicholas Copernicus was the first one to make observation of planets, and he didn't really agree that the Earth was at the center. He was thinking more like perfect circles and something more sun-centered, maybe heliocentric, but he was kind of too afraid of to publish because the church was in charge there, and they believed that the Earth was the center of the universe at the time. So he didn't really publish, but he was the first one to kind of come up with some ideas that maybe the Earth wasn't at the center. The next person that really helped move towards the sun-centered model was Tycho Brahe. He was friends with like a king or something, and he had lots of money, and he had this observatory, and he made very precise measurements of stars and planets around in the sky, in the night sky. But he couldn't really put the math to it, so he hired Johannes Kepler. And Johannes Kepler took these observations and put mathematical formulas to it. And Tycho, he was like, well, you're working for me, so I own all of your work. And he was trying to take credit for these laws that Kepler had come up with. Unfortunately for Tycho Brahe, who was not a very nice guy, he actually lost his nose in a duel, so he had a metal nose. And, well, unfortunately for him, he was at the king's table, and he had to go to the bathroom really bad, but it's very rude to leave the king's table. And, dinner with the king takes hours and hours and hours. Well, he didn't go to the bathroom, and he died like 3 days later of a bladder infection. So, if you have to go, go. So, luckily for Johannes Kepler, since Brahe died, he was able to take credit for his own work, and he still, it's like Tycho made these observations, but I did the math for it. So, he kind of proved mathematically these 3 laws that the sun is the center of our solar system, but it's not even the center of the universe, It's orbiting something else entirely. Now, they didn't really know that stuff back then, but that, these same laws work for everything else as well. Okay, so here's Kepler's 3 laws. These 3 laws I have broken down into the very simplest forms. They can be very complex. There's complex mathematics that go on behind it. This is kind of what you just need to understand. So, the first one says planets orbit in ellipses. This means they could be perfect circles, or they can be very elliptical circles. I don't know how much you've talked about this in your Algebra 2 courses, but here's an ellipse. It has 2 foci, and it orbits kind of like this. Now, the sun is going to be at one focus, and there's nothing at the second focus. So this planet is going to orbit around the sun in an ellipse. Now, the more circular it is, the closer these foci are to each other. And the more elliptical it is, it's going to turn into almost a straight line. So if they're super far apart, and it has practically no radius, that's when it starts to turn into a line. And there are a lot of different formulas and things that go along with this, which you'll learn in your Algebra 2 course probably next semester. But we don't need to know all that stuff. We just need to know that's an ellipse. There's nothing at this focus. The sun is the other focus. So that's the first law. Any questions on the first law so far? No. Okay, the next one is kind of complicated, a little bit. And it says that planets orbit equal areas in equal time, which sounds really nice, but you're like, what? What does that mean? That means that if you find an area of 2 points from here to here, and you calculate this area, and let's say this happens in 1 month, and you find that same area, you already know the area, so you need to know like this part. Let's say this part, this red part, and this part are the same area. If they're the same area, that means that it's going to travel from here to here in 1 month as well. So equal areas, equal time. This basically says that when it's closer to the sun, it's going to be going faster than when it's further away from the sun. Because here it has to travel all this distance in 1 month, and over here it's only going to travel this short distance in 1 month. So we're actually closer to the sun in January. Which you're thinking, but wait, it's cold in January. Well, that's because we're in the northern hemisphere. And when we're in the northern hemisphere, we're actually tilted away from the sun. So even though we're closer to the sun, we're tilted away. And that is why Australia's summer is so much warmer than ours, because they're close to the sun and they're tilted towards the sun at the same time. Now, our Earth doesn't circle quite this elliptical. It's actually almost a perfect circle. So the amount of change is very, very, very small. It's not going to look like our picture up here. It'll be practically a circle. Yes?
Okay, so I think you might know this is kind of really not related. But I read this morning that according to NASA, like from December 16th to the 22nd, it's supposed to be like dark. Like everywhere.
Why?
I don't remember what it said. I think it said something about like a shift in the Earth's rotation or something, and I don't know, it was freaking me out.
Okay.
Except for the 16th to 22nd, there's nothing but pitch black.
I'll look into it. I know that there is some serious solar flares going on right now, like the biggest sunspot they've seen in a long time. It is creating a lot of magnetic storms and stuff. That could be part of it, but I'll look into it. But I haven't heard anything.
I don't know if it was a hoax or what.
I'll look at it. I mean, darkness can be caused by lots of things. It could be, I guess Earth rotation, but that would have to be pretty major. More likely volcanic activity.
Yeah, because then they were like, we're preparing, we're going to make sure everybody has flashlights and all this.
Interesting. We'll see. I'll look at it. Okay. So, any questions on the second law? Second law. No questions. Okay. So let's move on to the third law, which is just this lovely equation. It has a couple of different forms. We're going to use this form. Another form that you might see is that t squared equals kr cubed or ka cubed, depending on what it is.
Wait, what was that?
T squared equals ka cubed. That's another form that you might see. It's more in the AP books than here. This is the form that we'll use. But if you're looking at the ka cubed, k is a constant depending on what you're orbiting. And A is the semi-major axis. But for us, we're just going to kind of simplify that. This is talking about these two objects, A and B, are orbiting the same thing. So you're basically doing a ratio. This A could be like the Earth, and this B could be Mars. So both of them are orbiting the Sun. So you take their orbital period, the ratio of the orbital period, and their distance from the Sun, the average distance. We're not going to worry about semi-major and semi-minor axes. We're just going to talk about it as an average distance. So you should have that equation. Is that a high five or is that a hand raise? Okay. Okay, this table here, you don't need to write this down. It's in your book. It'll be in Chapter 7, and it's also in the back of your book. This average radius is going to be useful when we're talking about like satellites, because this is the radius of the planet. So if you're talking about planets, you need to use the radius of the planet plus the height of that satellite, which we'll talk more about when we do satellites like tomorrow. This is the mass of the planet, or the Sun in this case, and this is the average distance from the Sun. So for today, you're going to probably stick mostly to this column. This is going to be, it's about this much from the Sun. And again, it's just kind of an average. It's already telling you basically the center of the Sun to the center of the planet. Any questions on that one? No? Okay. I'm going to do our practice for Kepler's laws real quick. And the first thing you want to do is read the question. It says, Io orbits Jupiter every 1.8 days at 4.2 units from the center. We don't really know what units it is or how long a unit is. It just says units. That's fine. Callisto orbits every 16.7 days. What is Callisto's distance from Jupiter in these same units? So we have 1.8 days, 4.2 units, and 16.7 days. Now, in case you're not really sure what it's talking about, Jupiter's a planet, so you know. Okay. And Io and Callisto are two of its moons that orbit around. Now, Jupiter has like 50-something, 60-something moons. But these are two of the main big moons. They're bigger than about the same size as Earth. Okay, so looking at these two things, we have Io and Callisto, so make sure you're thinking about that as well. We have something in days. What is this? Time close We need a little bit more specific time of what?
Day.
Nice guess, but no.
Year.
Close.
Revolution.
One revolution. So it's the time of one revolution, which we call period. So it's capital T. Now, what is this capital T talking about? Which planet or which moon? Io. So we're going to go the T of Io. Now it says 4.2 units. What is that? Units.
Distance.
It's distance. So it's going to be an R. And is it of Io or Callisto? Io. Good. And then 16.7 days. What's that?
Little T.
It's going to be a capital T, and it's the period of Callisto. I'll have you write the equation just in case you forgot, so you know. TA over TB squared equals RA over RB cubed. So it's got to be an R or a T. It's basically your choices. Okay, so now what I want you to do is, looking at this equation, I want you to go, instead of A's, we're going to put in Io. Now notice that Io's on top. It doesn't matter which one you put on top as long as they're both on top. Right? You can't do Io on top here and Callisto on top here. If you put Io on top here, it has to be on top there. Put Callisto on top, and Callisto needs to be on top again. Just make sure you're watching out for that. We're going to change B into Callisto. All right, what are we looking for? What's the question? The distance. So that's our R of what? Callisto. Good. So we're looking for RC. Now let's plug these numbers in. One thing that's nice about this equation is that it is just pretty much ratios. So your units are going to cancel out. So you don't need to convert into meters or seconds. All right, so let's do a little bit of a calculation here. We have 1.8 divided by 16.7 squared. Oh, I see how that happened. Divided by 16.7 squared gives us 0.0116. Notice that the days cross out, so this number is unitless. Over here, we're going to go 4.2 cubed and RC cubed. Notice I distributed the cube to both the top and the bottom there. It's important. And then I'm going to do a fancy little mathematical thing that I call flip-flop the top, bottom and the top. That way I can solve for RC, because when it's on the bottom down here, I can't solve. So it's going to be RC cubed equals 4.2 cubed over 0.0116. And I have RC cubed equals 6.3. We'll just round like that. I haven't cube rooted yet. I flip-flopped the bottom and the top. Basically, I brought RC cubed up here, and I took this number and put it down there.
What's the number that RC equals?
RC cubed is 6390.
Don't you have to cube root?
I will in a second, yeah.
Oh, that's what you said.
Yeah. I just want to make sure people caught it first. All right, and then cube root this number. And you're going to get RC equals 18.6, and that's going to go into units. We don't know what these units are, but that's your answer.
Can we put that in or put
No, we're not in enter clears, not this one.
I don't know. How do you get 6,390?
I did 4.2 cubed over 0.0116.
How do you do cube root?
A cube root? Let's. Here's how I do it. 5 cube root. That's going to be
I get that. That's so cute. Yeah, because we're at $4.
Okay, so any questions on the practice here? No? I have a new equation to show you. Newton's law of universal gravitation. This is the force between two objects. So it's it takes Newton's third law, where equal and opposite reactions, basically the dummies touching the tables touching the duck, equal force between the two, opposite direction. This is the same thing. So think about the force on the moon from the Earth and the Earth on the moon from the Earth, the force of the Earth on the moon. Something like that. Moon, Earth, moon, something. So the masses of these two objects, the distance between them, and this gravitational constant. Now, normally we find the weight of something on the Earth by just doing mass times gravity. But if you go up far enough away from Earth, as you move away, that gravity gets less and less and less and less. So instead of keep having to come up with constants, this is actually how they calculate. This 6.67 is actually a gravitational constant. It does not change like gravity does, where like gravity here on Earth is 9.8, but that on Jupiter is like 27.1 or something. So this does not change depending on location. So this one works for like the whole universe. So force is in newtons, mass is in kilograms, and R is in meters. A lot of times this will give you kilometers. Make sure you convert to meters before you plug it in, not after, before. And this G has these very strange units. Newton meters squared, kilograms squared.
What's the NM?
Newtons times meters squared over kilograms squared. Thank you. Okay, anybody more time to write that equation down? We're going to practice this equation real quick, just so that you have practice with scientific notation.
I like this.
All right, so let's read the problem. It says the mass of the Earth is a very large number in kilograms, and the mass of the moon is also a very large number in kilograms. If the distance between them is a very large number in meters, what is the force of gravitation between the Earth and the moon? So let's write down those numbers.
Can you write the formula on the board first?
Yes. It's going to be F equals G M over R squared. Where this is M1 and M2. There you go.
Does it matter which one's M1 and M2?
Nope.
Is this divided by?
All right. So let's write down these numbers. This says 5.97 times 10 to the 24 kilograms. This would be 7.35 times 10 to the 22nd kilograms, and 3.82 times 10 to the 8 meters. What's this kilograms thing? Mass. And how about this other kilogram thing? Mass. So we'll just label 1 and 2, doesn't matter which one's which. And then what's this meter thing? Distance. All right, let's plug. And what are we looking for? Force. This is what's the force. Okay, so plug this in. F equals 6.67 times 10 to the negative 11 times, actually, let's write it like this. I think it'll be easier for people. Times mass 1, 5.97 times 10 to the 24 times 7.35 times 10 to the 22 over.
These are all such big numbers. Wait, the G is over
3.82. Yeah, it doesn't matter because it's multiplied, so you can write it either way. I'm just showing you both ways.
So you can write it just the M1 M2 over R2.
Oh, that's just the equation.
And then multiply, yeah, because it's multiplied and divided. It doesn't matter what order you do it in. 3.82 times 10 to the 8 squared. Now, I would recommend using a 2-line calculator for this because not only is it very large scientific numbers, but if you make a mistake, it is really easy to go back and change one number. Whereas if you're using a 1-line calculator, going back is not really an option. It's not, really. So 6.67 times 10 to the negative 11 times 5.97 to the 24. Make sure you use parentheses. The way I've written it out here, you can do that pretty easily. 7.35 to the 22 divided by 3.82 to the 8 squared. All right, and I get 2 to the 20. That was my answer. So I want you to try this until you get 2 times 10 to the 20 newtons, just so you make sure you know how to use your calculator in scientific notation. And then I have one more problem for you, and then I have clicker questions. Or one more equation.
So you want us to do that one? Oh, no, we did that one.
I just want you to make sure that you're getting the same answer as me.
Do you need this still? It goes inside your Yes. Yeah, I do. Yeah, I really do. But ask someone else. Give someone all day. I was like my brother or something. No. Thank you. I was like my brother or something. I like Jared. Albert. We got one. You can. Oh, I don't know. He got fixed in my green. Mine's already in my I said my brother.
Is anyone still having problems? No? Okay, I want to show you this one last equation since people have to go to BCC.
No, we don't. Friday.
Oh. Okay, never mind. I'm still going to show it to you. It doesn't matter. All right, this is the last equation I'm going to show you for today. We're going to talk about this. We're going to talk about this a little bit more. Last equation for today. For today. Oh, this chapter is riddled with equations. Okay, so this one is basically puts Newton's law of gravitation together with Kepler's third law and comes up with this period equation. And that is the period of any object orbiting something is going to be equal to 2 pi times, so I know it kind of looks like 2 pi root, no, it's 2 pi times, so big parentheses, r cubed over g, and then the mass of whatever it's circling. So this is ms because it's like talking about planets orbiting the sun, but it works for if you're orbiting the Earth or if you're orbiting a giant black hole in the middle of the galaxy, something like that. So the mass is whatever is at the center.
And then we're square rooting that after?
Yeah, you do the distance cubed over the gravitational constant times whatever the mass that you're orbiting is, the square root of that, and then multiply it by 2 pi.
Okay. Oh, I got mine. What does T stand for?
The period. It's the time it takes for one orbit or one revolution.
Oh, are you?
All right. Does anybody need more time writing this down?
No. I do.
Okay. I just don't like the side conversations. I can't tell if that means you're finished or not.
Sure. That good.
Okay, I'm good.
Okay.
Thank you.
So here's the clicker questions. This is clicker question number 1. And it says Thermisto is one of Jupiter's moons that has an orbital period of 129.8 days.
Wait, so that would be
That would be period. That would be T, orbital period. The radius, that's your R, of Thermisto's orbit is 7,391,650 kilometers.
That's a lot.
Yeah. Carpo, which is another moon around Jupiter, has an orbital period of 458.6 days. How far away from Jupiter's center is Carpo? So you have the T of Thermisto in days, the R of Thermisto in kilometers, and the T of Carpo in days. And you're looking for the R of Carpo.
Hold on, I'm confused. So the T is for the other.
So
The
you
first
have
T is for the other planet.
T, R.
Okay.
And you're looking for the other R.
So we're using the TA over TV?
Yes, yes. Make sure when you assign which one's on top that if Thermisto's on top, put Thermisto on top on both sides.
The radius, that's the
distance, the
IO,
R.
right? The IO, whatever.
IO was just in the middle.
Oh, I'm
Should
saying,
be
would
square.
it be that should be A?
It doesn't matter which one you put. It's A and B.
Does it matter which one you square? You name
The days should be squared. The kilometers should be 2. Because kilometers is R.
So what is the T again? What does the T mean?
Orbital period.
It's for the revolution. So revolution. Sounds like revolution. But that would be the big T, right? So it would be 1. It's exactly like the problem we did before. Yeah, I don't remember that.
It's literally like
She's point probably.
what's your
A fox? Yes, fox? Isn't it? Oh,
I thought they only started making that
after. After what? After growth 4.0. He's like, the fox. But he's like 12. You never heard of that? You know about that? Not as often. No, I had. Because I'm a military base. They have it. Yeah. So, wait, on the right side of the equation, what is all of on the right side? You don't know. For either of them? No, you know for T, right? For thermisto?
Sure.
Yeah. So that big number.
Seth, go to guidance.
It goes on the bottom. Oh, you put yours on the bottom, didn't you? Did you put Callisto on the top? I mean, Carpo?
Technically, you should have a planner. You should sign that one.
Wait a sec, let me see if this is right now. Like, if it's wrong. Okay. What? You need it. Huh? Huh? I think. Yeah. Remember at the game,
Oh, now you're gonna keep it.
And you give us all like our Wait,
What do you keep doing?
I did one here. Blue one.
Some girls are
This also doesn't look like it's a
Miss Phillips, hurry, run away.
I did not
look
get
at the like the same side.
Oh, right here.
Is this right so far?
What did you get for your teeth?
This
You get it right?
And then once you solve for this, you can flip this up here and put this up here.
Oh, wait.
Anybody else want me to look at their work?
We found the answer and then we got it. No, we got it right.
I missed you.
I don't understand.
You're just trying to get his answer wrong so you can get the late pass.
Answer and then we have the right answer.
Hold on. I don't know what the right answer is. I got the right answer.
That's not the right answer.
Yes, it is. She confirmed it. I don't know how. Remember, that's it by itself.
You get it better.
4 plus 8.
It's just significantly, or it's just scientific notation. Like the equations are all just algebra and scientific notation. The actual concepts.
Wait,
this is
right.
why I tell them all the time.
I just worked so hard. This is not right. 7, 3.
Whatever you have in there, don't delete it. Let me look at it.
No, don't delete my stuff the way it is.
That would be the number.
No.
But that's what
Can you just do what I saw on your phone?
that's not.
Yeah, it's usually just like a small thing like that.
So this is going to be cute?
Oh no!
How can R just not be cute?
You can make it
Cube
cute.
it.
Yeah, you can't just forget that
Gotcha.
it's cute.
You have to divide by 20.
That is the stupidest thing possible.
So it is cute. I told you it was cute.
Because the R was right here.
Still didn't get it right.
No, wait, we got the right answer.
Still didn't get it right.
What did you get when you did this?
Equal.
Okay, I have 9 answers.
7.
Just so you know. Still waiting on more answers.
5, 0, over 0.802.
You have to cube it.
Why is it the bottom?
No, because
So
it's
you
the
got to
bottom.
redo it work.
Or do you have to cube it first?
Only talking about.
Do you cube this and then